Birth of the myth. German engineering culture and the roots of the idea of superiority. The story of German technical superiority does not begin in 1939 or with any single machine. It grows from decades of industrial tradition, national pride, and selective memory. To understand the myth, we must step back into the late 19th and early 20th centuries when Germany, after unification in 1871, invested heavily in education, technical schools, and industrial research. Universities created dense networks of engineers, chemists, and metallurgists. Companies like Krupp, Siemens, Daimler, and BMW developed reputations for skilled design and precise manufacturing. This long arc of industrial development created a cultural expectation. German products were associated with reliability, precision, and attention to detail. That expectation became a kind of brand. The phrase "made in Germany" before World War II could mean serious engineering excellence to many overseas buyers, but brand perception is not the same as wartime effectiveness. The myth of German superiority during WW II is partly an export of that pre-war reputation into the theater of total war. Add to that the spectacle of certain individual machines, tank designs that looked like they had been sculpted, aircraft with cutting-edge features, rockets decades ahead of many contemporaries, and you have the ingredients for a powerful story. Political factors also fed the myth. The Nazi regime loved grand narratives of national destiny, and the leadership was happy to broadcast technological triumphs as proof of superiority. Propaganda emphasized Wunderwaffen, secret weapons, and singular inventions like the V-2 rocket and the Tiger tank. When state-controlled newsreels, radio, and film showed stylized images of gleaming machines and acrobatic pilots, they did not present the messy reality of production shortages, maintenance issues, or tactical mismatches. For foreign audiences, selective German press coverage and captured propaganda reels could create a distorted impression, a country out-engineering its rivals. The myth also developed through psychological dynamics on the Allied side. Early German successes in 1939 to 1941 produced an understandable tendency to overestimate their capabilities. When a new German tank or plane first appears on a battlefield and performs dramatically, human observers generalize, inferring across categories. If one German tank is impressive, perhaps all German tanks are. If the Luftwaffe fighters dominate for a period, commentators may assume German planes are categorically superior. This is confirmation bias. Memorable successes stick, messy failures fade. Another important root of the myth is the difference between design innovation and wartime suitability. Engineers prize clever solutions, technical finesse, and the pursuit of performance. In peacetime markets, that pays off. But war demands more than elegance. It demands mass producibility, ease of repair, parts interchangeability, logistical simplicity, and training pipelines. The German industrial tradition often prized craftsmanship and high engineering standards, which could make a weapon excellent in controlled conditions, but fragile or complex in the field. The myth conflates engineering ingenuity with strategic effectiveness. To take a modern analogy, an artisan-made sports car may outperform a mass-market sedan on a test track. But if you need tens of thousands of vehicles that can be serviced in austere conditions, the sedan's simplicity can be an advantage. Cultural narratives also matter. For Americans watching documentaries or reading memoirs, a dramatic object is compelling. The Tiger tank's fearsome reputation translates into a simple story. German tanks were better. The real story is more subtle. A small number of very advanced tanks existed and were often deployed where they could make a psychological impact, but they were not numerically decisive. The idea of superiority persists because of storytelling. A handful of vivid examples create a coherent, memorable narrative. When historians or documentary makers select those examples without context, the myth hardens.
Finally, the myth is sustained by nostalgia and technological fetishism. There is an aesthetic appeal to German engineering, and collectors, hobbyists, and media amplify that appeal. Museums and restorers admire craftsmanship and the ingenuity of certain German designs, sometimes without foregrounding the logistical, doctrinal, and moral context that shaped how effective those designs were in war. The result is a layered narrative that blends factual technical brilliance with selective omission, a perfect environment for a myth to thrive. Exceptional machines and real innovations, what Germany actually produced and why it looked impressive. When people talk about German technical superiority, they usually point to particular machines, tanks like the Panther and Tiger, aircraft like the Messerschmitt Me-262 and Focke-Wulf FW-190, submarines such as the Type 7 U-boat and later the Type 21 U-boat, and the rocket programs culminating in the V-2. Each of these deserves careful examination. They were indeed impressive in various ways, but their strengths often coexisted with important limitations. Consider tanks. German armor in the late 1930s and early 1940s benefited from a coherent development path. Early Panzer divisions used reliable, well-balanced machines like the Panzer III and IV, supported by mobility-focused doctrine. With the Panther and Tiger series, German designers sought to restore battlefield parity against Soviet T-34s and KV series heavy tanks. The Panther combined excellent frontal armor and a powerful gun with good mobility and sloped armor, an advanced design for its time. The Tiger I, with thick armor and an 88mm gun, had unmatched firepower in many engagements. On the impression factor, Tigers and Panthers were awe-inspiring. A Tiger's frontal armor looked invulnerable to the common Allied guns early on. A Panther's sloping glacis and 75mm gun could destroy many opponents at long ranges. The visual and battlefield spectacle reinforced beliefs in technical dominance. But beneath the spectacle were problems. Both machines were heavy, complex, and maintenance-intensive. The Tiger's final drive and suspension systems were prone to damage under extended field use. Manufacturing a Tiger consumed far more resources and skilled labor than producing a larger number of medium tanks. The Panther, rushed into service in 1943, suffered from mechanical teething problems, including engine and transmission failures. These issues reduced their operational availability and increased demands on logistics. Aircraft present a similar mixed picture. The Messerschmitt Bf-109 family and the FW-190 were world-class fighters in their time. They combined high power-to-weight ratios with solid airframe design and excellent engine performance for the late 1930s and early 1940s. In 1944-1945, the Messerschmitt Me-262 jet fighter represented a generational leap. It was faster than any Allied piston engine fighter and carried potent armament. The Me-262's existence suggested German breakthroughs in aeronautics, but the jet program was hampered by production delays, fuel shortages, inadequate pilot training, and a corrupt and politicized procurement process. Where a jet could have dominated in numbers and strategic effect, it appeared in small, late-war batches too late to change the outcome. Submarines tell another layered story. German U-boats dominated the early Battle of the Atlantic and posed a real threat to Allied shipping. German designers understood the operational environment and optimized the Type 7 for long patrols and mass production. Early Wolfpack tactics exploited intelligence and communication protocols to devastating effect. Later, the Type 21 Electro boat promised a submarine revolution, improved submerged speed, streamlined hulls, and greater endurance underwater. The Type 21's design foreshadowed modern post-war submarines. Yet these technological achievements could not overcome manpower shortages, Allied advances in anti-submarine warfare, improved radar and code breaking. Many late-war Type 21 boats were built too late to be operationally significant and suffered workmanship problems due to hurried assembly under bombing.
The V-2 rocket program is a quintessentially complex case. It was a technical marvel, the first large ballistic missile, a true forerunner of space-age rocketry. Engineers solved difficult problems in propulsion, guidance, and materials under wartime constraints. The V-2's flight demonstrated clear technical prowess, but the strategic impact was limited and morally fraught. V-2s were expensive to build relative to the limited military effect they produced, and their deployment consumed resources and human lives in production under brutal forced labor conditions. From a purely technical history standpoint, The V-2's legacy is enormous, but as a wartime weapon, its cost-effectiveness and ethical consequences complicate any narrative of simple superiority. Small arms, optics, and other technologies contribute to the impression of German superiority. German tanks and aircraft often featured highly accurate optics, and the Germans developed advanced rangefinders, sights, and radio gear. German small arms like the Karabiner 98K were reliable bolt-action rifles, and the MG-34 and MG-42 machine guns were high-rate-of-fire designs that influenced post-war firearms. The MG-42 in particular was a manufacturable, reliable design that inspired many post-war machine guns. Yet, such innovations had trade-offs. The MG-34 was sophisticated and expensive. The later MG-42 was simpler but more brutal in its manufacturing methods, reflecting wartime adaptation. A recurring theme is that German designs often focused on performance metrics, armor thickness, muzzle velocity, top speed, sometimes at the expense of simplicity and ease of production. In a mechanized war where attrition and spare parts matter, design elegance must be matched by mass producibility and logistical rationality. The German emphasis on engineering excellence resulted in machines that could outperform adversaries in specific engagements, but that were costly, difficult to produce in large numbers, and often fragile in non-ideal conditions. That is not a denial of ingenuity. Rather, it is a clarification. Engineering achievement does not equate to strategic or operational superiority when the full context of wartime demands is taken into account. Production, logistics, and numbers. Why technology alone was not enough. A decisive factor in WW2 outcomes was industrial capacity and logistics. Wars are ultimately contests of production, supply, and sustainment. The Allies, and the United States in particular, mobilized immense industrial power. Vast numbers of tanks, aircraft, trucks, and ships poured into different theaters. Germany's industrial model and wartime strategy were less suited to converting engineering excellence into sustained warfighting capacity at scale. First, compare industrial base and resource access. Germany had a sophisticated industrial sector, but limited access to raw materials relative to the Allied bloc. Steel, oil, and rubber shortages constrained German production choices. Strategic bombing and Allied interdiction further disrupted supply lines and manufacturing capacity. The United States' industrial output dwarfed Germany's. Thousands of aircraft a month, tens of thousands of tanks and trucks produced over the war. Influence from geography played a role too. The U.S. industrial base was largely secure behind oceans. Germany faced bombing from 1942 onward and had limited secure zones for mass production. Second, production philosophy diverged. German pre-war industry prized precision and craftsmanship. Many German wartime weapons were manufactured with tight tolerances and high-skilled labor input. This produced high-quality items, but limited throughput. By contrast, U.S. and Soviet production emphasized standardization and mass production techniques that traded some refinement for enormous output and interchangeability. The Soviet T-34 is a textbook example. Designed with simplicity and robustness in mind, good mobility, sloped armor, a potent 72.6mm gun in early variants, the T-34 could be produced in large numbers, repaired rapidly in the field, and accepted in large quantities by crews. The T-34's value was not only technical, it was the combination of good design and mass production that made it decisive on the Eastern Front.
Third, logistics and spare parts are operational multipliers. A superior tank sitting in a depot is strategically irrelevant. Tanks that break down require parts, trained mechanics, fuel, and recovery vehicles. German complex designs often demanded specialized parts and skilled technicians. Allied logistics emphasized redundancy and the ability to cannibalize and repair vehicles quickly. By 1944, Allied logistical superiority was evident. Fuel pipelines in Western Europe, massive shipborne supply trains, and efficient maintenance systems meant that Allied units often stayed supplied, whereas German units increasingly faced fuel shortages, parts shortages, and abandoned equipment. Fourth, the numbers game matters in attrition warfare. In the long run, sheer quantity can overwhelm quality. If one side can replace losses at scale, it can absorb tactical setbacks and continue to press. Germany's smaller population and industrial base made sustained replacements harder. Even when German units had superior equipment in certain sectors,
Attrition eroded their advantage. The Eastern Front exemplified this. German tactical proficiency and equipment quality could win engagements, but the Soviet ability to field larger numbers gradually ground down German forces. Fifth, the allocation of resources within Germany was sometimes inefficient. Political interference in military procurement created distortions. Competing branches of the Wehrmacht and the Nazi bureaucracy often duplicated efforts, sponsored rival projects, or prioritized prestige weapons over mass-producible systems. Resources poured into experimental projects that produced limited battlefield returns. The focus on exotic wonder weapons sometimes diverted materials and skilled labor from more impactful mass production lines. Finally, the impact of strategic bombing cannot be overstated. Allied bombing campaigns progressively degraded German manufacturing capacity, disrupted transportation networks, and forced dispersion of factories into smaller, less efficient sites. The bombing campaign, combined with interdiction of oil supplies and the loss of resource-rich territories, shrank Germany's ability to scale up production. Even brilliant designs could not reach the quantities or reliability required to change the strategic balance when the production base itself was degraded. Thus, when we talk about the myth of German superiority, production and logistics are central counters. Technology mattered, but in a total war environment, industrial capacity and sustainment determine how much technology can be applied and for how long. A handful of excellent machines cannot substitute for a well-fed, well-supplied army supplied with tens of thousands of reliable and maintainable vehicles. Doctrine, human factors, and operational reality, how equipment performed in the field. Machines are only as effective as the doctrine, training, and human systems that employ them. The Wehrmacht's early successes in 1939 to 1941 owed as much to combined arms doctrine, initiative at lower ranks, and effective use of mobility, radios, and logistics as to any single superior technology. Conversely, by 1943 to 45, deteriorating training standards, shortages of experienced crews, and mismatches between doctrine and reality increasingly undermined the fighting power of even technically advanced equipment. Start with doctrine. German Blitzkrieg, shorthand for combined arms maneuver, rapid assaults, and operational-level coordination, was revolutionary in its integration of armor, air power, and motorized infantry in 1939 to 1940. Radio-equipped tanks and decentralized command allowed for flexible responses and aggressive exploitation of breakthroughs. These doctrinal elements amplified the effectiveness of German equipment. A well-trained crew in a medium tank with clear mission objectives could execute maneuvers that outclassed numerically superior but doctrinally uncoordinated opponents. However, doctrine evolved and strained under new conditions. The Eastern Front demanded different tactics. Vast distances, harsh climates, and deep reserves of manpower tested operational concepts. German forces, designed and trained for maneuver warfare in narrower theaters, struggled to adapt fully. Defensive operations, attrition warfare, and prolonged sieges exposed deficiencies in supply, winterization, and reserve depth. In such conditions, the tactical advantages of individual machines became less decisive. Training and human factors are critical. In early war, German crew training was thorough. Experienced NCOs and officers provided capable leadership. As casualty rates rose and training periods were shortened, the average skill level dropped. Complex machines required trained operators and maintainers. As Germany lost experienced personnel and rushed inexperienced recruits into service, the very advantages of sophisticated designs eroded. Examples abound. A high-performance tank gun is useless without a gunner who can range and maintain it. A jet fighter is limited by pilot skill in high-speed combat. Human performance, the ability to perform under stress, maintain equipment, and execute doctrine, is often the decisive variable. Operational realities also introduced environmental and supply constraints. The winter of 1941 to 42 exposed German equipment to extreme cold that clogged engines and brittled fuel lines. Maintenance in mud and snow increased wear and reduced operational readiness. The tactical decisions to stretch supply lines or to prioritize certain theaters over others had consequences for which machines could be effectively used. The German reliance on extended supply lines to support armored thrusts left units vulnerable when supply trucks could not reach forward units. Allied adaptation should be considered. Early German successes prompted innovation among the Allies: better tanks, improved anti-tank weapons, more effective air tactics, and better combined arms. Where the Germans had local superiority, Allied learning and industrial response narrowed those advantages. The development of more powerful Allied tank guns, better organized artillery, and improved air-ground coordination gradually mitigated German technical edges. The human ability to adapt and innovate under pressure is a crucial counterpoint to any one nation's technological leads. Case studies illustrate the interplay of doctrine, human factors, and equipment. In North Africa, German and Italian forces initially used tanks and mobile units effectively in desert maneuver warfare, but issues of supply, spare parts, and air superiority shaped the outcome. In the Kursk salient in 1943, German heavy tanks and assault guns faced massive Soviet defenses. Ingenuity and individual tank performance were insufficient to pierce fortified belts backed by huge reserves in artillery. In the Ardennes offensive of 1944, German tactical surprise relied on concentrated armor and bold maneuver, but fuel shortages, poor weather limiting air cover, and inexperienced crews reduced the operation's chances. Ultimately, equipment is necessary but not sufficient. The myth of German superiority often abstracts machines from the complex systems around them: doctrine, training, logistics, maintenance, morale, and strategic reserve. Where those systems were strong, German equipment performed admirably. Where they were weak, even the finest machinery could not compensate.
Memory, myth-making, and lessons for today. How the myth lives on and what it teaches us. The myth of German technical superiority in WW2 survives in museums, documentaries, reenactments, and popular culture. It persists because of a mix of aesthetic admiration, narrative simplicity, and the human preference for stories featuring exceptional characters and objects. But checking the myth against the historical record reveals nuanced lessons for modern military thinking and public memory. First, memory is selective. Histories condense complexity into memorable episodes. A documentary might focus on the Tiger tank's battlefield dominance, without examining how many Tigers were lost to mechanical failure or left stranded for lack of fuel. Military enthusiasts prioritize engineering features because they are tangible and visually compelling. This creates a skewed archive. Photographs of pristine German tanks in museums feed into an impression of ubiquitous superiority, even as archival logistics reports tell a different story. Second, myths can obscure moral and strategic realities. Celebrating technical brilliance without acknowledging the political regime that financed and directed the technology risks sanitizing history. German engineering successes were embedded within a state that pursued aggressive expansionism and committed atrocities. Any responsible recounting must avoid uncritical praise and situate technological achievement within ethical and strategic contexts. That is why the neutral, respectful tone requested for this script is important. Technical admiration can be separated from moral endorsement by showing the full picture. Third, the myth offers practical lessons for modern force design. Contemporary militaries frequently face the same tensions between high-performance, high-cost systems and cheaper, more numerous, more maintainable alternatives. The WW2 example highlights important trade-offs. Invest in a few technologically superior platforms that can dominate tactically, or invest in mass-producible, robust systems that ensure survivability under attrition. The correct choice depends on strategic objectives, likely fight intensity, resupply possibilities, and political tolerance for risk. Policymakers today should weigh the WW2 lessons carefully. Elegance and technical advantage must be balanced with logistical resilience, production scalability, and ease of maintenance. Fourth, intelligence and perception management play roles. During WW2, exaggerated intelligence reports and propaganda amplified perceptions of German prowess. In modern information environments, the amplification of certain technologies can distort public understanding of military balance. Critical evaluation of sources and attention to the whole system, training, doctrine, logistics, remain essential.
Fifth, the myth's persistence reflects a deeper human fascination, the romance of the machine. Tanks, jets, and rockets appeal to imaginations across cultures. They become symbols in stories about bravery, innovation, and national identity. That fascination is not inherently wrong, but it becomes problematic when it replaces rigorous analysis. A balanced narrative honors the ingenuity while also explaining limits, consequences, and the broader context. To a modern American audience, the story should prompt humility and curiosity. Admire the engineering, but ask the tougher questions. How many of these machines were available when it mattered? How easy were they to repair? What were the human and material costs of building them? How did doctrine and logistics shape their success or failure? These questions turn a myth into an educational tool. In closing, the myth of German technical superiority is a partial truth dressed as a total one. Germany produced genuinely advanced and sometimes world-leading weapons and systems during WW2, driven by a strong engineering culture and significant scientific achievements. But technical brilliance alone did not win wars. The decisive variables in WW2 were industrial capacity, logistics, doctrine, training, operational adaptability, and political decisions. Where German engineering achieved remarkable things, it often did so at the cost of numbers, maintainability, and strategic coherence. The myth persists because vivid machines make compelling stories. The counter-myth, that logistics and quantity matter, is less cinematic, but crucial for understanding how wars are won or lost. For a long-form documentary-style script aimed at an American audience, the narrative arc should pair technical description with human stories, operational context, and strategic analysis. Show a Tiger or an M262 in full technical detail. Then follow with the story of a crew struggling to keep the machine operational, or the strategic consequence of diverting resources into a prestige project. Use comparisons, T-34 versus Panther, mass-produced Allied fighters versus complex late-war German jets, to anchor the technical discussion in concrete outcomes. That approach respects your audience's interest in machines, while providing the fuller, harder-to-dramatize truth that in war, the combination of people, supply, process, and production matters more than any single piece of equipment. This is not a story of denial. It is a story of balance. German engineering in WW2 was real and sometimes brilliant. The myth of blanket superiority is not. By examining machines in their full operational, industrial, and moral contexts, we gain a more accurate, richer, and ultimately more instructive understanding of history, one that honors technical achievement while refusing to let it obscure the realities of war.